In the last video, we had gone so far as to define average velocity, which is defined as the change in the position between two events over the change in time between those two events for some object. So now what we'd like to do is dive in more to define what the velocity is at some instant. Now, experimentally, you'll only ever be able to measure the average velocity, to be clear. You'll always have to measure the position at two places, measure the time that the object was at those two positions, and then use that to figure out the average velocity for that interval. And that's as good as we can ever do. But it's very useful to think about as an ideal, how could we define the velocity at a particular instant, thus instantaneous velocity. So in the picture I have drawn here, what I have is a graph of the position that some object occupied as a function of time. And first thing I would just ask you to do is think for just a moment and ask yourself, which way is the object moving? Okay, hopefully we agree that the object is moving to the left. We can get this by seeing that all we have plotted here is an x-coordinate, so that tells us that things are happening in right-left. Since I didn't specify that left was positive or anything weird like that, the 8 meters would mean that the object was 8 meters to the right of the origin initially, and then with time, that position decreases. And so we get closer and closer to the origin. So this means the object is moving to the left. Okay, so since I said that experimentally, we can only ever truly measure an average velocity. What I've done with this data is I've boxed off some points. I've got a pair of points in pink, I've got a pair of points in green, I've got a pair of points in blue. And I would like you to ask yourself, if what I am trying to do is characterize as closely as possible what is happening at exactly t equals 3 seconds, the point I have circled, which pair of points do you think would give me an average value that's the closest to what's actually happening at exactly t equals 3 seconds? So go ahead, pause that, think about it for a bit, and then we'll get back together. Okay, so it turns out that the pair of points that are the best pair to use are going to be the blue points. Here, this means that and this is because the object just hasn't had that much time to change how it's moving. At 2.5 seconds and 3.5 seconds, what I have drawn here, how the object is moving probably isn't all that different from what it was doing at exactly 3 seconds. On the other hand, really sorry about that. On the other hand, for the green pair, for instance, those are located at 1 and 5 seconds. That's a lot farther away in time, so you've had more time to change. And the pink pair at 0 and 6 seconds, that's even farther away in time from the time that we actually care about. And so the object would have had the largest amount of time to change how it was moving. So this is our recipe here, is we can imagine that although maybe you'll get lucky with numbers in certain specific cases, in general, approximations that take a pair of points that are farther, that cover a bigger time span around the time we care about, will generally be worse than approximations that flank a smaller time span around the point we care about. So what we can do is we can imagine just taking this to its logical extreme. we can imagine just letting the time interval that flanks the point we care about get ever smaller and smaller. So we still keep looking at a position and a time on either side of the time that we actually care about. And we can define the instantaneous velocity at a specific time. So no bar here, that means instantaneous velocity. Again, the triple equal sign just means by definition. To be the limit as delta t approaches 0 of delta x over delta t. So this is saying pick a pair of points that flank the point that you care about, calculate the average velocity. Pick another pair of points that flank it more closely, calculate the average velocity again. Pick another pair of points that flank it even more closely, calculate the average velocity again, and so forth. Now, what mathematicians have proven is that for anything that would describe how things would actually move in nature, as the time interval gets ever smaller and smaller and smaller that we're using to flank the time we care about, eventually they prove that the first digit in the value quits changing. That after that point, no matter, as you keep making the time interval smaller, 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 that first digit will never change again. And then as you keep making that time interval ever smaller, 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 and calculating average velocities again and again, eventually the second digit quits changing, and then the third, and then the fourth, and so forth. So the idea here is that you can just keep this process going until you have as many digits as you care about. And so that is how we define the instantaneous velocity. So you just imagine we keep taking a sequence of average velocities for ever smaller and smaller time intervals flanking the time we care about, and eventually we'll get as many digits as we need, and those digits will never change again, and then we can move on with the problem. So it's probably helpful, though, to think about how we can represent this graphically. So let's say here that I go ahead and, here we go, make a plot of position versus time here. And let me just draw a curve that is representing how our object is moving. Maybe it's doing something like that. And let's say that right here at this time, I want to know how fast is the object going. Well, if we follow our recipe, we think about what this would mean graphically. Let's start first with that pink pair of points. The pink pair of points would represent some fairly large time interval that flanks them. I would calculate the change in position, which would be the rise, divide that by the change in time, which would be the run. So what I can do is I can graphically calculate, say that the average velocity for that time interval would be equal to the slope. So that would be, whoops, not V bar. So that would be the average velocity over that time interval. Okie doke. So then we can go ahead and maybe go and take a smaller time interval. Let's just jump right ahead to, say, the green one. So the green one would look something like this. And again, it would be the same process. Now you can see here, the slope of this is different than the slope of that line segment. So this is where we expect to get different numbers. But I could continue this process and go with ever smaller and smaller intervals. And if you think about it, what's eventually happening here is that our left point is moving into the time we care about. Let's just mark that time we care about with a black dot. and our right point is also moving in towards the black dot. So the logical end of this would be when the 2 points wind up becoming that one same point. Okay. So graphically, what would that look like? Graphically, that would correspond to striking a tangent line at the point we care about. And then we will say that the slope of the tangent line is equal to our instantaneous velocity at that time. So how do you strike a tangent line? So if you're doing this graphically, the way you strike a tangent line is you go ahead and you lay a ruler down so that it's touching at the time you care about. Probably a little easier if you do this with a clear ruler, but not vital. And then you move it back, you just twist it back and forth around that point. Eventually you'll get it so that the ruler doesn't cross through the line anywhere else. And I'm not saying like way down the curve. Like for instance, if we follow this long enough, it would cross through here. That doesn't count. Just talking in the neighborhood. As you twist it around, eventually you'll find that the ruler is only touching the curve at one exact point. And then you just go ahead and draw that line, and that would be the tangent line to the curve at that point. And the slope of that tangent line would be the instantaneous velocity at that time. Okay. So while we're continuing to do things graphically, we can go and look at how we could do the reverse process. So now let's say I have a graph of velocity with respect to time. How could I find the displacement? In the last video, we knew how to do that for uniform motion. So just as a quick reminder of how that worked. Say I had a plot of velocity versus time, like so. Let's say the object was moving uniformly, which means the velocity was a constant. We then said that if I wanted to know the displacement that was associated with this time interval delta t, what we worked out was that the displacement was equal to the area under the curve, with the caveat that if the area is if the velocity line is under the t-axis, then the area that you would make would be negative. Now this doesn't find us the position, it finds us the displacement, so we need to know where the object was, well, technically at one specific point in time, but usually in physics what we have is at the beginning of the interval. And so with that, we could then figure out where the object ended up. But now we're ready to go ahead and extend this idea to, sorry about that, there we go, velocities that aren't a constant. So let's go and do that. So the idea is going to go like this. So here is my velocity as a function of time. And let's just say it's doing something like that. Now, for what I'm going to be describing, mathematicians would have an awful lot of caveats. However, those caveats aren't going to be necessary for any function that actually describes something that happens in nature. So if you've run across this in what I'm about to do in some prior math class, what I'm doing is legit for the kinds of functions that we worry about in physics. So the idea is that we look at this and we go, geez, I've got no clue how to do that. But what I could imagine doing is making like a little zigzaggy curve. like this. Here, let me do a little better with that. So what I can imagine doing is I can divide this into a bunch. Here, let's try that. I can imagine dividing this into a bunch of time intervals. And I'll just do a few just to get the flavor of it. So I go and look here. I know that if I were to do this area here from this point all the way down to the axis, that area would be an overestimate of the displacement because the object wasn't going as fast as this for the whole interval. Likewise, if I were to use the lowest velocity, the area I would get underneath would be an underestimate. So it's probably more reasonable to do is just to split the difference between the two. So you use that interval. So you go ahead and make a little stair step like that. And then we repeat the same game in the next time interval. We'll say, all right, yeah, that looks pretty middling right there. And then we do that here and say, maybe you're right about like that, something like that. And then the idea is in each of these small little time segments, you can go ahead and calculate the displacement. So this would be the displacement in the first time segment. This would be the displacement in the second time segment. This would be the displacement in the third time segment. And what you do is you just add them up for however far you need to go, say maybe out to here at time t. Well, you look at that and you say, well, that seems a little sketchy. So you're basically approximating by saying, well, first we'll move at whatever the average velocity was at one particular interval, and then the next, and then the next. Calculate these displacements, but I can imagine that this isn't going to be exactly right. To which I'd say, okay, that seems fair. So if you want, you could make these intervals smaller. And by making them smaller, what that will do is it'll make the zigzags less pronounced. Instead of the zigzags that we have going along here as we're drawing our boxes, looking like this, now maybe if we're doing it on smaller intervals, those zigzags are maybe doing something like that. So a little better behaved, looking more like what it's doing. And then you can say, well, that's still, I'm not entirely convinced, so I can just go ahead and say, okay, keep that up. As you keep making the time intervals ever smaller, those zigzags will get ever finer. Eventually, the zigzags will get so fine that we're zigging and zagging within pixels on your monitor. And at that point, your eye can't tell the difference. And at that point, instead of having this area of these boxes, what you would end up having is this area under the curve. Now, mathematicians have proven that if you keep this kind of sequence up, where you keep making finer and finer straight line zigzag segments to approximate our function around the curve, eventually it'll be the same deal. The first digit will quit changing, and then the second digit will quit changing, then the third, and so forth. And so the limit of it turns out to be just plain the area under the curve. So now finding the area under the curve in a lot of circumstances is beyond the scope of this course, because you would have to use the methods of calculus, and this is an algebra-based presentation. But there are ways you can do it. For instance, if you did have something that looked exactly like this, what you could do is you could print this out on a piece of paper, glue stick it down onto a piece of cardboard, X-Acto knife out the shape, and weigh it. And then you weigh another piece that you construct the same way that is, say, 1 meter per second high by 1 second wide or something like that, look at the ratio of the weights that you weighed, and that would tell you the area of the section that you cut out. You could certainly do it that way. There's also a device that draftsmen have called a planimeter, where you can follow the curve and a whole bunch of funny little curves and dials change, and out pops the number. So there's all sorts of ways that you can do it. However, for anything that we're going to be concerned about here, I'm going to just be focusing on things where we can break it into nice clean segments and just break it into nice geometric figures, and then we can calculate the areas of those geometric figures. So let's just do a quick example of that just to get a flavor for that. So let's say that we have, let's say a car. So we have a car that was speeding up steadily. So from a standing start. So at time 0, it was at t equals 0, and then we'll say at t equals 10 seconds, our car was moving at, let's say 20 meters per second. Yeah, sure. All right, so, and we'll say that it steadily picked up speed to get to that point. So what we can do is we can go ahead and draw the function. So if we're steadily picking up speed, that's going to be a straight line. And so then we can find the distance we traveled by finding the area of this triangle right here. So the change in position, the displacement, will be equal to the area under the curve. You'll see me write AUC a lot whenever I need to do this kind of thing. So now we can just remember from when we took geometry way back in the day that the area of a triangle is 1/2 the base times the height. So here the base is 10 seconds and the height is 20 meters per second. So our car has moved 100 meters. Now I know I say this is an area under a curve, and you're saying, but wait a minute, your units are just units of length. Yeah, this is a funny area. So here, this horizontal axis has dimensions of seconds. This vertical axis has dimensions of meters per second. If I multiply those two together to get the area under the curve, the dimension, the unit that I'm left with is just meters. But there you go. And that's the sort of thing, you know, maybe you might have segments, and for a lot of applications, that's all you really need, is we can find some segments where we can just break things into square, triangles, and rectangles, and take it from there. Alrighty, in the next video, we will go ahead and take a look at acceleration.